So we're very excited to have today Daniel Tartakovsky. So I brought him here just to entertain me for a day, something like that, right? So Daniel has been at Stanford for the last 3.5 years or so, many years at the University of San Diego, and Los Alamos before. And before that, it's a secret, a top secret, I cannot share. So with all that, we would be pleased to hear him talking on the method of distributions for hyperbolic conservation laws with random inputs.
All right. So thank you for the invitation to Nicholas primarily, and thank you for your time being here so late in the afternoon. So the reason for this title is that I thought it was a mathematical seminar. Otherwise, it didn't have to be so scary or off-putting sounding. But anyway, I think some of you who are observant might think that you saw me here a few months ago. That was my brother. And Nicholas asked me to give a talk that is longer than my brother's, which was very short, apparently. So that's why I'm saying this stuff to kill in time. No, so I could do longer, right? After, or I'll have to stop at 5.
5:10, the maximum.
Okay. So anyway, let's get going. And so this is really UQ talk, right? And maybe in this audience and this center, it doesn't. I'm preaching to the choir, but it is a general problem or tenant in computational science. The more we rely on predictive models, the more problems arise that very often we get pictures that, or even sometimes movies, and they could be blood flow, could be anything. And we tend to believe because of the movies that what we see is what actually happens in reality. And that, of course, is not the case. And the question that this National Academy of Sciences convened the committee, and the question that they asked, how do we make sense of the modeling output? And in old days, we could use, or we did, we would use data and experiments to validate our models. But more and more, we rely on models for which there is no data, right? So that is true, say, in astrophysics, when we look far away into the sky. This whole field of UQ actually started with in the Department of Energy when after they ratified the nuclear test ban treaty, right? So all of a sudden we couldn't test our weapons, and therefore you have to rely on models to ensure that the weapons are still operational. Right? And so once they started relying on models, then reliability and uncertainty in predictions became paramount. So that's where it came about, and that's why the answer that this committee came up with is essentially says that we cannot rely on any model predictions unless these model predictions come with error bars, just like you would have with experiments. And perhaps more importantly, they pointed out that this uncertainty quantification has to be probabilistic. Okay, and that's sort of great, but that's relatively recent. And then there is, because if you dig deeper, you will see that this is David Hume, almost 300 years ago, understood the importance of uncertainty, and having Alex and Nicholas here, I'm sure ancient Greek philosophers said something like that many millennia ago. But so the point that we have to deal with uncertainty, that's been with us for a long time. The reason we didn't want to do it is another question. Okay, but so how do we, what actually, if you want to do it probabilistically, how do we do that? And so the way we do it is like that. So suppose that you have a parameter that is heterogeneous due to natural variability or manufacturing variability. And what we have is just a few measurements of that field, right? And then you know that at points where you don't have measurements, that your parameter could really have any value, perhaps could not be negative or things like that. But then if you were to ask to run a model with a parameter like that, you couldn't do it, right? Because you need to provide the value at every element for your code to work. So you have to guess what values to use, and that's an ill-posed problem. You just cannot do it. So one way of dealing with it is to say, okay, I have this parameter, I don't know what the values are, could be maybe anything, some is more likely than the other. And so once you start talking about likely or less likely, then probability is a useful tool. So you would say that your parameter theta is a random field. Where do you get statistics for that random field? Well, you get it from these measurements. Sometimes it works, sometimes it doesn't. So there is something that's called the ergodicity hypothesis that allows you to interchange spatial mean, spatial statistics with ensemble statistics. So that's a separate story for maybe another talk for machine learning. I'm not going to talk about that. So we suppose that these data are sufficient to parameterize our parameters in a probabilistic sense, right? So we need to know correlation structure, mean variance, and ideally the full distribution. Okay? But so once you have a parameter that is a random field, then no matter what problem you are trying to solve, could be as basic as diffusion equation, heat conduction equation, it becomes random, right? Because you have random coefficients. And so if you don't know values of your parameter at a certain point, that means that you cannot know the value of your solution at that point. And so what that tells you is that there are infinitely many possible solutions. And again, some of these solutions are more likely, some are less likely. And so therefore, you don't have a unique solution to your problem anymore. That's, I think, is the key point, of course. And instead of all this infinite but countable number of solutions, that they're characterized by this probability density function. Yes, so you say that you need to know what solution, what value of u, so your state variable, is more likely and less likely. And so that you get by having the PDF probability density function, or equivalently cumulative distribution function. So that's CDF is an integral of the PDF, of course, right? Or very often in engineering applications, this is too hard. So people would say, I want to compute the mean. That would be my best prediction. And then I want to compute the variance of my system state. That would be a measure of predictive uncertainty. Okay, so now the question is, so that's the goal of uncertainty quantification, yes, to compute those distributions of the moments. Okay, but then shortly, actually not shortly, but at the same time that the nuclear bomb was developed at Los Alamos, Monte Carlo methods appeared, right? For the same reason that they had to deal with uncertainties. And so Monte Carlo is a great technique in the sense that it's easy to implement. You don't need to go to school to do it. It works beautifully on large machines because it's embarrassingly parallel. So it's all great. But the disadvantages are, first of all, you cannot get a PhD in UQ doing basic Monte Carlo, so you need to do something smarter. But also utilitarian, right? So it has a slow rate of convergence, relatively slow rate. And by that I mean that it converges as 1 over square root of the number of realizations, number of times that you need to run your model. Okay? And so that slow rate of convergence is the whole reason for being of uncertainty quantification. So in what follows when I tell you that this particular UQ technique doesn't work, what I mean is that it is not faster than embarrassingly, that's a brute force Monte Carlo, because there is no reason to use fancy methods if they are slower than Monte Carlo, because we have this floor, we just want to improve on it. Okay, so that's I think one of the key points to take away from this, right? So this UQ is a field where there is a very simple tool and it's very robust. We just want to improve on it. Okay? Okay, so what, just sort of a brief history of what did people try to improve on this Monte Carlo method. So historically, the first method, and it dates back to Fish and Papa Nicolau and all kinds of people 60, 50 years ago. So it's a moment differential equations method. So you say, if what I want from my Monte Carlo is the mean of my system state and the variance, I want to try and derive deterministic equations for these two quantities of interest. And then I just solve them, just two equations, and I'll be done instead of solving thousands. Okay, that's great. And because it could be very computationally cheap, right? So you get a huge computational speed up. But it has a number of other advantages, one of which is that you get, it provides you with a physical insight into the system. So for example, if you take your stochastic differential equation and you average it by hand, you will see that your mean equation would always be non-local, or at least in the vast majority of cases, unless there is some zero white noise or whatever. And so this has been known for 50, 60 years until recently some of our colleagues rediscovered the non-locality. But that's because they are not aware of this history in this. And by the way, this is just a matter of relabeling. So people didn't call it UQ. They would call it stochastic homogenization, another name for this field. Okay? But what's the practical disadvantage of that is that you need closure approximations for this method to work. And these closures, most often than not, that they were carried out by perturbation expansions, and that's done in terms of the variances of the input parameters. Yeah, so when you do perturbation expansions, you want your perturbation parameter to be small. Yeah, so it worked for small degrees of heterogeneity or uncertainty. It's actually has been shown that it works for variances of log parameters very often, and then up to 4, so you could extend the range of that through different various reduction techniques, but that's the sort of impetus for other UQ methods where people would say, we want to get non-perturbative methods. Okay, and so what are these non-perturbative methods? So there was 20 years ago a lot of work on alternative techniques. They came in waves, like fashion. So first people did one method, then the next, so forth. And the advantage were of those methods were that many of these methods were non-intrusive, like stochastic collocation methods. Nicholas was one of the pioneers of that method. And so, but essentially stochastic collocation becomes like a sampling technique. Only you sample smarter, so that's how you beat Monte Carlo, right? So you need fewer runs of your forward code. That's the idea. But then there turned out to be some issues. Like one of them was what's the curse of dimensionality. So if the correlation length of your input parameter is sufficiently small, then I would say stochastic collocation doesn't work in the sense that I defined earlier. So your method could become slower than Monte Carlo. And that's especially true when you have, say, shocks that move through your system. That's the types of, or in general, when you have hyperbolic problems. So which is the focus of my talk. And by the way, if you have questions, feel free to ask and interrupt. Okay. And so then what I want to talk about today is a method that is tailor-made for hyperbolic problems. And even more than that, it works best for systems with either uncorrelated inputs, like white noise, or short correlation lengths. So that's because they are more accurate in those regimes, and these methods do not suffer from curse of dimensionality, the method that I that I will present today. So how do they work? How do they do that? Well, because we want to avoid this approximation. We don't do carpooling wave expansions. And what we want to do instead is we want to derive one single deterministic equation for the full distribution of our, for the PDF or CDF of our state. Okay, then we have to solve just one equation, not 1,000 times the underlying equation. Okay, so once we have these full distributions, we could compute probabilities of rare events and things of that nature. Okay, there is a price to pay, of course, and you will see this throughout my talk. So there are closure approximations that are needed to derive these equations, and that's where you could do that either in a classical way by sort of going back to what's been done in stochastic homogenization, or maybe you could learn these closures with neural networks. And I'll briefly discuss both approaches. Okay, so what class of problems I'll be talking about today? So we looked at other problems as well, but I'll stick with these problems. So what we have here is potentially a system of hyperbolic conservation laws, right? So we have a flux here that depends on the state variable. We have reaction terms here, and what's uncertain here, in addition to initial and boundary conditions, we also have parameters in each of these functions. Okay, so this could be uncertain, and the formulation is sufficiently general in that we could handle PDEs with random coefficients that could be well correlated in general, but we could also handle SPDEs if this incorporates a source term that has white lines. Okay, and so the idea here is actually comes from statistical physics. It's unfortunately misattributed to another colleague of Nicholas, whose name I will not mention, but it goes back way before him to some physicists in Sweden who did it. So the idea is like that. So suppose delta is a delta function here, right? And u is our state variable that satisfies those differential equations, right? So it's uncertain and random, and capital U is a number a value that it could take at the point x and t, right? So it's a deterministic value, and U here is a random quantity. So let's take the ensemble mean of pi. So it's denoted either by E or by the brackets here. So if you have a general function, pi over your random variable, so how do you compute the mean? Well, you multiply it by the cumulative distribution, by the PDF of U, and you integrate, right? But now if you plug delta into here and use the property, like basic fundamental property or definition of the delta function, what you get is this. So in other words, the average of this delta function is the PDF of our solution. Okay? And so it suggests then the two-step procedure. So we start with our equation, with the governing equation, hyperbolic equation, and we follow two steps, right? So the first, starting with this equation, we derive an equation for pi, and then we average this equation, and we get in U equation, deterministic equation for the probability density function. And then we solve it, and we are done. We get a full distribution. Okay, so we could also do that naturally for CDFs. So that's something that I think has not been done in this context. So instead of a delta function, you could of course say, okay, why don't we use a Heaviside function? Because if you use a Heaviside function and you average it, you will see that you get a cumulative distribution function. So cumulative distribution functions, they are S-shaped objects. They are usually much easier to solve for numerically, right? Because it's an easy, nice and smooth function, monotonically increasing. So the CDF method works exactly like that. First you derive an equation for pi, and then you average it. Okay? So today I will walk you through 3 examples. from different fields of sciences or engineering. So first is advection reaction problem, where you have C here is, say, concentration, and it's being advected in the random velocity field V, and then it undergoes, say, chemical reactions. Okay, so what's uncertain here is maybe reaction rate and the flow velocity. Okay? So the second problem is a shallow water equation, Saint-Venant equation. And what we have here, say, H is the height of water, and Q of H is the flow velocity, flux, that is proportional to, it's a function of H. In this model, they are related like that. And then you could also have some reaction terms that account for loss of water, maybe tributaries or drains, whatever. Okay, so what's uncertain here? Well, this coefficient alpha, which in this shallow water framework, that's say roughness of the surface over which the water flows. Okay, these problems are listed here in order of difficulty because this is a weakly nonlinear problem in the sense that the nonlinearity is in the source term. This here is fully nonlinear, but it admits smooth solutions, so it's easy, relatively easy to handle. And then a more challenging problem is Berger's equation, where Vs is just S, so it's S ds dx, or Buckley-Leverett, where you have an arbitrary non-monotonic function of the state variable, and that of course describes many things in fluid mechanics, in traffic problems, all kinds of things, right? And the difficulty here is that the systems develop shocks. So handling these problems with standard UQ methods could be challenging. Okay, so let's start with the first problem, yes, advection reaction. Destroying the church property. So advection diffusion equation, again, V is random, alpha is random. Again, we want to, let's derive a cumulative equation for the cumulative distribution function, the deterministic equation. So there is again, just remember, pi is the Heaviside function of our random, say C is concentration. Its average over all realizations of C is the cumulative distribution function of C. And by the way, the cumulative distribution function, by its very definition, what it tells us, it's the probability that our solution is smaller than this value C, capital C. Okay? And that's why it's a smooth function, because as C becomes capital C becomes larger and larger, the probability that your solution is smaller than C increases, right? And eventually, as capital C becomes infinity, the probability is 1. Yeah, so that's how it works. But so just because for this function here, you could see that if you take the derivative with respect to time of pi, so you use this chain rule, and you get this result. So this step is important, right? There is because when you write d pi dc, so this is a Frichet derivative, right? Your C is a function, so that's a functional derivative. It's problematic, but because this is a function just of C minus small capital C minus small c, you could say that the derivative with respect to minus C, small c, is minus the derivative with respect to capital C. And capital C acts here just as a coordinate, so this is good. Okay, so you could do the same thing with the divergence here. And then with the delta function, why you could not use just any arbitrary function? Because we also use this Tifting property of the delta function. That if you have a delta function, capital C minus small c, you multiply any function of small c, it's the same as that you could replace small c with capital C. Okay, that's just a basic property of the delta function. And it's important because small c we don't know, it's an unknown solution, but capital C we know, it's a coordinate that varies for concentration, say from 0 to 1, from 0 to infinity. Right, but and so you could see that each term here, so you have dc dt multiplied by d pi dc, this divergence multiplied by d pi dc, and R multiplied by d pi dc. So what it tells us is that if we take our governing equation, multiply it with d pi dc, and then you use these properties, and what you end up with is this nice equation here, right? So this equation became linear. We started with a nonlinear problem that had reaction term, and we projected it in a higher dimensional space, right? Because now this capital pi is not just a function of x1, x2, x3, but it's also a function of this x4, which is capital C. Right? And so this is a very nice equation. It's easy to solve on a computer or analytically, right? Because it's linear. There could be nothing simpler than that, right? And so but that completes the first step of the method. We have an equation for capital pi. So now we need to average it. But there are different ways of averaging it. One of them could be just using Monte Carlo on this problem, because it's linear, it's trivial. But maybe we could do something better. We want to derive a deterministic equation. Okay, so, and we know how to do it if we took a class in turbulence, right? Because you would immediately recognize that this equation is just the advection of a passive scalar in a random velocity field. So this problem has been studied to death in all kinds of ways. And so one of them, that again, there are many people who claim ownership, but it goes all the way back to Krejcman and in the, maybe not 40s, but 50s. So we know that the average of this equation, if you localize it, so if you don't, you get this fully space-time non-local differential equations for the CDF. You could do that. But you could also localize them if you want to do it as an approximation. And you will get this, sorry, I'm getting ahead of myself. So this you don't make any approximations, right? If you just plug this expansion into here, take the mean, you get something that looks like that. But then here you have random fluctuations, and this is what in turbulence that looks like Reynolds stress, right? So that thing needs to be approximated, and this is exactly what Krejcman approximated. And that term here is an approximation that gives rise to this dispersion or diffusion of the CDF. Okay, so it's known how to do it, and under these coefficients here, they depend on statistical properties of your inputs. So the mean, variance, and the correlation structure. So they are computable in closed form. Everything is good. The Green's function. So it's all good, and it's linear. So you could solve this one equation and get a solution. Okay, so we did that, and again, remember that we started with this weakly nonlinear equation where the coefficients could have been, as you can see here, so they could have had a delta function for the correlation. So potentially it's infinitely dimensional stochastic problem. And that's where I was saying that having white noise is actually beneficial here, because for that problem, these integrals are computable analytically, so you get a huge speed up in computation. So it's really good for white noise. And more importantly, what you could see, so this method does not suffer from the curse of dimensionality, and it also does not suffer from this long-term integration problem. So you could see the solution here remains accurate as you march in time. Okay, so the same thing with the Saint-Venant equation. So Saint-Venant equation, again, highly nonlinear, because the flux, it depends on the state variable. But it has smooth solutions, that's important. So we use the CDF equation, the same tricks. You get step one, you get exactly the same equation as we had before. The only difference is that now your random velocity has a different shape. But your nonlinear SPD in D dimensions became linear in D+1 dimension. Okay, so we average that because it's exactly the same equation. You get exactly the same problem, the same CDF equation, right? With the same closure, just as you saw before. So we could handle very easily these kinds of problems. And not surprisingly, you get accurate solutions. So there are whenever you see these disagreements, it's because there are different ways to compute those integrals, and some of them are more accurate than others. So that this is just what we have different ways, and you compare it with Monte Carlo, so that you get an accurate solution for the cumulative distribution function. Okay, but now let's look at the harder problem where we have shocks. So think of the Burger's equation, but this is harder because the coefficient here is sort of the ratio of polynomials. So you have a non-monotonic behavior here. Flow velocity on the solution. So this solution certainly has shocks, that's why people study it. And these shocks satisfy this entropy condition, right? Where essentially a discontinuity of the state variable and its fluxes and the ratio of that. So that gives you an equation for the dynamic of the shock. And to the left, behind the shock and ahead of the shock, we have smooth solutions. So this is what's known in general about these problems, right? If you were to take a PDE class. So it doesn't matter whether it's stochastic or not. But so if you start with this equation here, and you again multiply everything by pi, and do the stuff that I mentioned, you would again arrive to the same equation, right? D plus one dimensional linear equation. You take the mean, you get the same advection diffusion equation. And in general, it's great, except neither this equation nor this equation can support shocks because these are linear equations. So something must be wrong, right? Because these equations don't know anything about shocks. So how did we get? The first way of getting around it is to say, but actually you could already guess why it didn't work, right? Because the equation with discontinuities, with shocks, does not make sense. You cannot use it for at points where your solution is discontinuous, right? So in general, these equations make sense only in the weak sense. But if you want to, if you could use your entropy condition and say, okay, these solutions are perfectly great, or equations, where solutions are smooth, we could use this method. But then what we need to do is we need to keep track of the shock. And then the idea then here is to say, if I have the shock that moves with random velocity because things are uncertain, then what I now have is a joint probability density function between the state variable, which is random, and the position of the shock. So it's a joint PDF. But that joint PDF you could decompose into a conditional PDF times the PDF of the shock. But I have this Rankin-Hugenow condition for the shock. So I could compute the PDF of the shock either exactly or numerically by solving that PDE or ODE. And so then for each value, for each trajectory, each position of the shock, I could compute the conditional PDF by using that method. And then the joint distribution is like that. And then if I want to compute the PDF of my solution, it's just the marginal of the joint distribution. Okay? And it works pretty well as long as you use a proper closure here. That's comparison with Monte Carlo. And that's a little, the graph is a little busy because there are different ways of computing those closures, and I didn't walk you through all of them because it's not the point of here. But if you pick a proper closure, you get an accurate solution that matches Monte Carlo. So that's the point. Okay? But as we discussed earlier, here that is a little it would not. So that's somewhat unsatisfying because that method that I just presented to you, while it works very well, it requires the knowledge of the shock dynamics. And if I know the shock dynamics and these problems, it's half of the job. So I don't want to have a method that requires an analytical computation of the shock dynamics. So then say, okay, what can we do here? And let's look again at this problem, potentially with shocks. Let's use the equation for pi. And instead of having this equation here, where we d pi dt plus, so instead of having this advection of a passive scalar, so we could add this unknown function m, which is still a linear problem because it depends on capital U is the coordinate, x is the coordinate, time is time. And so when we got to that point, we were actually, well, or at least I was, maybe not my students, very proud of myself that we figured out how to handle shocks or deal with these problems in the probabilistic sense until somebody pointed out to me that in a totally different context of deterministic equations, and not even of solving deterministic equations, but in the context of proving uniqueness and existence of solutions with shocks, these guys, I think one of them is a Fields medalist, right? So they came up with exactly this idea, and they did it quite some time ago. Okay, and again, so they did it for proof purposes. So this m is not computable, but what is known about m is that it's unique, that it's proven, and it's finite, and it's not negative, non-negative. Okay, so these are basic properties that are known about this function in the deterministic context, right? But it's sort of okay if you could take the mean, and it's not much glory here, but nevertheless that's what we did. But the question now, how, if we are interested in computing and not proving, how do we compute this unknown m? Okay, and so again, so another thing that is known is that if you, by the way, so this is called the kinetic formulation of hyperbolic conservation laws. Like that's what these guys call it. Kinetic theory of hyperbolic conservation. Okay, and again, if everything that I showed you before is correct, and it actually turned out to be sort of a satisfying part, so this m has been proven to be 0 if your solutions are smooth. And that's why everything I presented before worked nicely. And then, otherwise, it satisfies these properties. And then under certain conditions, in some regimes, you could compute this m analytically. Okay? And that's great because that we could at least sort of validate some of our techniques here on these simple cases. Okay? Right? So, this is an example from a traffic model where this flux depends on the state variable as a second degree polynomial. And this is a good problem because for this particular problem with the proper choice of the initial condition, you could compute this m, or therefore its average analytically. So we've done that. And that's how the solutions look like. We could reproduce a rarefaction. So if you think of a traffic model, so if you have say traffic lights, you have a discontinuity in the initial condition where, say, behind the traffic you have no cars, and then ahead of the traffic you have a lot of cars, and then that's your initial condition. Then the time starts running. So what happens? You have rarefaction where all the cars in front left, and there are no cars in the back, or maybe little. So you don't have any shocks. Nice situation. That's rarefaction. You could have shocks if you reverse the situation where you have a lot of cars looking at the traffic and relatively few cars ahead. You develop shock. So we could reproduce all of that, and there is no error in this method. So that for regardless of whether you have white noise or not. And what's interesting here is that this method allows us to capture highly non-Gaussian and non-trivial distributions of the system state. So if you look, this is the PDF of our solution. So there is no way to capture this in any known UQ method, I think. Like it's a very weird one, right? It's totally not how you would expect the PDF to look like. Okay, but what do we do in cases where we do not have means to derive this M analytically? So we know that it exists, we know that it's unique, but we need to estimate it somehow. So how do we estimate it? Well, we could estimate it from data. So the data could come from a few Monte Carlo simulations, or maybe it could come from observations. Okay? And so there we found a way of assimilate data that because note that these equations are for the probability density function, right? Or this is CDF. And so therefore it really lends itself to Bayesian updating, because you already have a full distribution. And so one way to assimilate data into these problems is, instead of doing like say ensemble Kalman filter or Bayesian updating, you could do what is known in this data assimilation business as a Newtonian relaxation, where you say this F is the PDF or CDF of the observations. You're subtracting the CDF of the observations and your unknown CDF that you are trying to estimate, and you multiply it by alpha. So this parameter alpha, what it tells you is that if you have a lot of good observations, so you would say lambda is very large, so your dynamics doesn't really matter, and so your F that you are trying to estimate is given by the CDF of observations. And then if you have bad data or few data points, then you take lambda relaxation coefficient to be very small, so you just focus on the dynamics of the CDF. Okay? And right, so this is one way, and we and there are proofs actually. There are proofs of convergence that if you have enough data, then you will converge. F will converge to observations in the L1 norm, and a lot of good stuff is known about this method. But what's good is that you could see here, just by inspecting these two equations, that this is a way, machine learning way, to learn this M, that hitherto was unknown and uncomputable. It's just this term here. That's how we would get a closure. Okay, so that's one way of getting this closure. Okay, and it's a good way. The reason, the advantage of using it in the CDF framework is that we could allow very easily for measurement noise, for all kinds of things. We could also use agent data, agent-based data. Like so you say if you think about traffic density, instead of talking about traffic density, maybe you have GPS on individual cars, so you could keep the trajectories of each cars and to build the observation. So it's a powerful technique, but the downside is that you really need to have a lot of observations for this to work, at least in our experiments. So that's the reason that we thought, okay, maybe we could do something else. And another impetus for that's a great technique that was used, like say maybe 20, 30 years ago. And now there is a new name for data assimilation, it's machine learning, right? So we thought we need to do machine learning too. Because Nicholas is doing it, everybody's doing it. So we implemented, actually Nicholas's technique here, but in this way. So again, we want to learn this unknown function here. It's a linear function, right, of the three-dimensional function. But because it's a linear equation, I know that its solution here could be represented as the linear combination or superposition of two solutions. One is the solution, the CDF for the smooth solution, which is computable, but it would keep track of a lot of things that happen in the system. And then there is the second part, which is this kinetic defect, what is known here, right? So that reflects the information about the shock. And so what we want to learn is this term, rather than learning this. Okay, because we thought that putting some knowledge here would make it easier to learn that thing. And then how do we approximate this kinetic defect? It's just a known function of three variables, right? So what we used a deep neural network approximator for this unknown function. And then we found the coefficients in that interpolator approximator by minimizing the residual. So we don't claim any novelty here. It's exactly what say Nicholas has done. But the results look like that. So what you see here so what we plot here is the normalized errors in this estimation of that coefficient as a function of time. And the light stuff here corresponds to the time for which we have data. So essentially, we trained our model in this part, and then let it be predictive in that part, in the darker part, right? Advanced it in time. And then we are looking here, new here is the sampling frequency in space and time. So how many samples in the time coordinate you had, or in x coordinate. Okay? So that's what we did. And so what you could observe here, in general, that this machine learning technique, at least in our implementation, so I'm not making any general claims about accuracy or whatnot, but in our implementation, so in the training regime, we managed to learn what that function is, and it worked okay, but then the simulation error, as you do extrapolation, and that maybe is the problem. So we are not trying to fill in the gaps in between model runs. This is really in the predictive regime where we extrapolated our interpolator, our neural network representation of M. And so, needless to say, the error grows with time. What's also clear here that the rate of growth depends on the type of data that you have. So it makes more sense to sample in time than in space, to have more frequent sampling in time than in space, but that's maybe to be expected if we are extrapolating in time. Okay, but so that's our limited successes in a foray in this neural networks. And so this is then. I will stop here as a summary then. So the basic idea, again, so this, I think, sort of takeaway messages here is that number one is that if you want to be in the UQ business, I think the goal for doing anything you're doing in UQ is to beat Monte Carlo, to be faster than Monte Carlo. And so what we claim is that the CDF method is under many conditions achieves that, and especially if you have smooth solutions. It's a great technique. I highly recommend it. It's a great method for white noise problems, and in that sense it's complementary to other UQ techniques, like say connotation methods and other polynomial chaos expansions based methods. And so for that reason, I think it's a great alternative to other techniques. And then the work in with machine learning of these closures, it's ongoing. We have better results. In fact, if you have a steady state problem, then we have great results for when we don't need to interpolate in time. If we just have nonlinear ODEs or PDEs where there is no time and we just learn in the domain X and Y or Z, it works great because in the interpolation regime, everything is good and this M function that we need there is computable. But once we add time, then we have this growth of the error. So I'll stop here and please ask me questions.
Yeah, so I think, granted, I'm kind of extrapolating here based on my past experience, but so it seems in general this process that essentially you're kind of arriving at this averaged quantity equation, and you have this additional closure model, and kind of basing off experience in fluids. Something I'm not seeing here, I'm wondering, is once you introduce that model, you kind of open the can of worms of model uncertainty, of which, like what you show with the shock, you can have variable levels of accuracy depending on what you choose. So how exactly do you account for introducing that?
So that's a really good question, and the answer to that is what I mentioned earlier about this method being exact for white noise. So it turns out that the closure, like if you like say if you average this equation where random velocity v here is white noise, so no correlations, so infinitely dimensional problem. So this equation is exact, and there is a proof to that in many papers by Krajcman. And in fact, this equation, when the correlation is finite, not zero, so you could think of like these coefficients, you could think of their derivation as sort of a perturbation expansion in the correlation lengths relative to the size of your computational domain. And this is precisely the sense that I mentioned this method to be complementary to polynomial chaos-based methods, because it's a great tool for short-range for inputs with short-range correlations. Okay, so we used it, for example, for say if you have Langevin problems with colored noise, so you could use that and it works beautifully. But as correlation lengths become very large, this approximation becomes worse and worse. So that's one part of the answer. So the second one, and this may be what we discussed earlier today. So you don't have to use this closure at all, because maybe you could just look at this, and we also have done that. Not maybe you could just use Monte Carlo on this linear equation, because it's a linear, beautiful equation. You could use it with the method, use method of characteristics to solve it, right? And just compute you use a kernel density estimator on the Monte Carlo realizations of this equation for pi. So then you don't introduce any closure problems at all, right? There is no issue with any of that stuff, right? But again, what's important though is that you get this equation cannot support shocks because it's a linear equation. So you need to be cognizant of the presence of discontinuities.
Have you looked at, or can a method be applied to integral differential equations?
For questions like that, I could just say yes. I don't know, we didn't apply that. So the reason the hyperbolic is in the title is because if you add second order derivatives, that becomes more complicated. And that goes back to this. So if you think, if you look at these types of equations, so you could see that this equation is essentially what you would expect a Fokker-Planck equation to look like, right? It's a deterministic equation for the PDF, the Fokker-Planck equation. So once, if you add the Laplacian, and maybe if you add integrals, so what we've done that, what you end up with is something that looks like a Boltzmann equation. And that's why I asked you about Boltzmann equation, because you end up with coefficients here that would depend on the moments of f. And so it's non-linear that way, right? Because the coefficients are the integrals of the solution. So if you start with an integral differential equation, give me an example. Not right now. Email me an example. I'd like to try. Maybe it does, maybe it doesn't. I don't know. But it could work, and probably would if you approximate your integral with Gaussian points or whatever, and then you have higher dimensional. Yeah. So that's something that we tried, and then maybe use SVD to reduce the dimensionality.
All right, I don't see any other questions. Thank you, Daniel, for visiting us.
Thank you for your time.